네, 오늘 저희 세미나에 지금 MIT에 여러분들도 잘 알고 계시는 그 케빈 첸 교수님 연구실에 그 박사과정 이제 거의 마지막 해를 보내고 계시는 우리 김수한 연구원님을 모셨는데요. 어, 사실 올 초군요. 작년이 아니라 작년이구나. 작년 말에 그 MRS 때 저희가 이제 그 보스턴에 방문을 했었는데 그때 케빈 첸 교수님 연구실에 방문했었고 그때 김수환 연구원님이 굉장히 저희를 잘 가이드 해주셔가지고 굉장히 감사하는 마음을 계속 가지고 있었습니다. 근데 또 연구까지 너무 잘하셔가지고 그래서 또 저희 윤종환 박사님도 또 한번 추천을 해주시고 하셔서 저희가 이 기회에 세미나를 한번 모셨으면 했는데, 시간 내서 지금 저녁 8시신 거죠, 거기는?
아, 예, 맞습니다.
늦은 시간에도 시간 내주셔서 이렇게 세미나에 와주셔서 감사합니다. 어, 저희, 김수환 연구원님의 양력을 아주 간단하게 소개를 해드리면, 아시는 것처럼 지금 현재는 MIT에, 그리고 소속은 뭐라고 해야 될까? 전자전산 정도에 해당되겠죠?
예, 저희는 전자컴퓨터공학부 정도로 쓰고
어쨌든
있습니다.
예, 어쨌든 ECS에 속해 계시고요. 그리고 지금 케빈 첸 교수님 연구실 거기 다일렉트릭 일러스토머를 이용을 해서 굉장히 소프트 로봇을 굉장히 연구를 잘 하시는 분이시죠. 그래서 그 연구실에 박사과정으로 계시고 어, 주로 연구하시는 연구 분야는 아마 논문에서 보신 학생도 계실 거예요. 소프트 로봇, 특히 플라잉 로봇이나 아니면 굉장히 그 작은 스케일의 마이크로 로보틱스에 굉장히 좋은 연구들을 많이 하고 계시고요. 공부는 대학은 한국의 그 서울대학교에서 공부를 하셨고요. 그다음에 석사학위는 카네기 멜론에서 받으시고 지금 MIT에서 박사과정 하고 계십니다. 그래서 지금 뭐 논문들에서 많이 보실 것 같아서 굉장히 좋은 논문들의 논문 퍼블리시도 하고 계시고 또 좋은 연구를 하시다가 보니까 또 우리 로보틱스 분야에 굉장히 좋은 학술지들의 또 논문 리뷰에도 많이 참여하시고 하는 것 같습니다. 어, 오늘 발표하시는 내용은 여러분들이 다 알고 계실 것으로 알고 있는데요. 이 다일렉트릭 일러스토머를 이용을 해서 다양한 이런 소프트 로보틱스 시스템에 이용하는 것 소개해 주실 예정입니다. 제가 소개드린 모든 걸 다 포함해서 큰 박수로 김수환 연구원님 환영해 주시면 감사하겠습니다.
감사합니다. 교수님 혹시 그 영어로 진행을 하면 될까요?
네, 편하신 대로 하시면 됩니다.
아, 예,
저희가
그
여기
외국분들,
접속한 학생 중에 외국인 학생들도 있어서 영어로 해주시면 더 감사하고요. 편하신 대로 하시면
네,
됩니다.
그 영어로 하다가 영어 좀 막히면 한국어를 좀 섞어서 해보도록
네,
하겠습니다.
한국어로밖에 할 수 없는 표현이 있다면 한국어로 하셔도 돼요.
네,
그리고
알겠습니다.
혹시라도 제가 미리 양해를 드리면 한 시간까지 걸리지는 않겠지만 제가 10시에 또 다른 일정이 있어서 혹시라도 길어지게 되면 제가 중간에 좀 나가더라도 양해를 부탁드리겠습니다.
아, 예, 알겠습니다.
네, 감사합니다.
아, 예. All right, thank you so much, everyone. My name is Suan Kim. As Professor Kyung has introduced, I'm in fifth year in my PhD at MIT ECS, working with Professor Kevin Chen. And first of all, thank you so much for inviting me to such a prestigious seminar. Especially, I'm very excited to present my work in front of all the DA related researchers. So today I'll be introducing our lab's work on insect scale flying robots powered by soft actuators. So from the title slide, we can see several keywords out here. First of all, insect scale, and then second thing is flying robot, and then the last thing is soft actuators. So I'd like to begin by introducing some of different scales of robots. So nowadays, I would say it's like the era of emerging robots. So we have a ton of robot in different scales. For instance, if we see the scales of a meters, we can think of robots something like MIT Cheetah. So MIT Cheetah robot was developed by Korean professor Sang-bae Kim at MIT, and then this is around like 1 meter robot with four legs that has broke the record when it first came out, especially in terms of like locomotion speed. And then if we get to like larger sizes, what we can think of like in the scale of like tens of meters, I would say is like this airplanes. So airplanes are, we don't really usually call it as robotic systems, but I think this is a great robot that we use in our daily life. So which is in the length scale of like maybe like 20 meters to 40 meters, I guess. And then since this robot is way larger, this can accommodate way more capacity, especially like using as transportation method. And then if we get to even larger robots, we can think something like aircraft carriers. In Korean, it's 항공모함. So these ones are even larger that this one can even accommodate multiple of airplanes. So as the size goes larger, basically the force that the robots can generate is way larger, has different use cases. But on the other hand, I think there are smaller robots that has unique usage from the larger robots as well. For instance, if we get to 10 to the negative one of order of meters, which is 10 centimeter, I want to introduce like this robot, which the crate fly. So I don't know how much have you seen crate flies here, but crate fly is something around like palm-sized robots, maybe like 15 centimeter each. And then this has like payload capacity of only around like 15 grams, and then the operation time of like maybe around like 10 minutes. So way different from our large like aircraft. But since those are very small, lightweight, like especially in research labs, they use this crate fly pretty actively, especially doing control swarms and all the flight tests. So if it goes smaller, it has different usage, but it also has very unique usage that we can't really use like larger robots in our lab spaces. Even smaller, especially if we get to very small scale, I also want to introduce like this robot, this tiny robot out here. So right now, maybe I'll switch the pointer. So what you see over here is a head of an ant. It's a little larger ant, honestly, but this is still a head of an ant. And then over here is four-legged robot. So this was actually developed by my master's advisor, Professor Sarah Berkbrider at Carnegie Mellon University. And then the way this robot works is that this robot has like magnets on its feet. And then we can apply external magnetic fields so that we can operate the magnetic legs. So this is still tiny, but this all have like four legs, and then this can like go across the very cluttered space, and then maybe potential use case of like climbing inside our body. But of course, this is very small that it's different from the others in a sense that this one really doesn't have board or batteries or any other sensings or controls on board, but it's all relying on off-board powers and then controls. So from my perspective, something in the middle or something in compromise is something in the centimeter scale. This robot you're seeing right now is called Hammer Robot from Harvard, especially Professor Robert Wood at Harvard. And then this robot, just like Cheetah, has four legs. Each leg has 2 degrees of freedom, and then they all have controllability with control boards and batteries and everything on board. And then if you can reference the coins, it's around like 2 to 3 coin size, which is maybe around like 5 centimeters. So I would say from state of the art, like this size robot, this size range is where we can make the robot with fully autonomous systems. To summarize this all things, when it comes to smaller robots, it has very unique usage, I would say, but still, what's the challenge right now? It is very hard to build things in small scales. Then what is really hard to build things in small scale? What comes first in my mind is something like this. So what we are seeing right now is this is assembly of four-chamber piston engine that we typically use in our cars. So say if we imagine if you have to shrink down the engine by like times of tens or times of hundreds, what happens is that we'll have to make or fabricate each component by 10 times smaller or 100 times smaller, which is already pretty challenging. And then what we'll have to do next is that we'll have to assemble those manually to make it to like four-chamber engine, which is almost a nightmare, right? So this is practically what makes it really hard for us to make small systems compared to larger systems. So obviously we have to make system much simpler. But on top of these practical issues, there are some physics, underlying physics that indicates that physics are changing by the size of the robots. So I took the example of these drones as we are making flying robots. So say if you want to size down the drone by 10 times or 100 times with the characteristic length of L, let's see what happens. First of all, what I want to see is the body weight. So if we assume it's roughly the assumption and it's the rough scaling, but if we assume that the density is kind of similar, the weight might scale by L to the cubic, obviously. But one important component of the robots are joints. And then the joint friction is usually, say, if we have like lubrication friction, we usually say the lubrication friction scales by L to the square. So what we can calculate here is that if we divide this joint friction by the weight, the friction to the weight scales to L to the negative 1. And what this means here is that L to the negative 1 means that if L goes smaller, this number goes larger. So what it means is that when the robot goes smaller, typically the joint friction is getting much larger relatively. And then this indicates ultimately that if we get smaller size, what we will need is maybe we'll need some different joint structure other than friction-based joints, rotating joints. We can do something similar to the actuators. By the way, if you have any questions, please let me know during, please feel free to interrupt anytime. We can do similar thing from the actuators, especially the electromagnetic motors that we are using. The motor power also scales by L to the cubic as well, but the motor friction is also something in the lubrication friction area which scales by L to the square. So actually what happens for the DC motors is that the motor efficiency drops by a lot when the motor goes down. And then that's partially the reason that we can't use motors for smaller drones as well. What it means is that ultimately, if we want to make smaller system, we'll need some sort of different power density mechanism other than motors. Another part is the controls. So if we roughly scale the robot inertia, which is m times r square, which will scale by L to the order of 5. Whereas the body torque, if we just roughly scale it by mg times r, which will scale by L to the order of 4. The rotational acceleration is also scaling by L to the negative 1, which means when the size goes down, the rotational acceleration is much faster, which is pretty apparent, right? And then that means we will need much faster control system as well. In fact, our robot right now uses like kilohertz of controls. And then some other things are like computations are going much limited, battery power and capacity going much limited. Whereas like position sensing, relative like error of the position sensing will go larger, which all suggests that the system side, it's pretty much limited to make the small system at this point. Then how we approach to make smaller system, especially for us, we get a lot of inspiration from insects in nature. Right now, what you're seeing right now is bumblebees. So if you compare the structure of bumblebee to the existing drones, first of all, it seems it's much more like compact. Of course, the size is way much smaller. And then what you can also see is like this only has two wings, which is much simpler than the drone structure with four propellers. So overall, what we think is that nature has some sort of hint that we can shrink down the size as well as simplify the system as well. If we take bumblebees and if we start seeing this as the robotic systems, and then what we can observe is that, first of all, it has a pair of wings. And then in the base of the wings, what it has like all the flight muscles and joints. And then of course, it has like all the sensings and then all the computations on its body and energy storage in its body. And at the end, the bumblebee weighs around like 120 milligrams. And then the wing beat is typically around like 200 hertz-ish. So the robot we are building has pretty similar structure where we have pair of biomimetic wings, and then we have uh, artificial muscle in the middle, which is DEA, which is your pretty familiar to your lab. And then we all have like the compliant joint systems that is different from friction-based joint, which can be very efficient in small scales. And then our robot right now weighs around 0.16 or 160 milligrams, and then wing beats around like 300 to 400 hertz. I would like to go a little deep to the structure of the robot. So we have like our joint structure has two different features. So the first thing is so-called linear four-bar transmission system. So what you can think is this is the four-bar system with linear actuator in one side. So over here, you can see this red block is moving linearly, whereas this end tip is rotating from the fixed joint. So what you can think is that our actuator is pushing and pulling this red block, and then our wing is attached to this red beam so that it can rotate. And then, in fact, we are not actually making this in this rotating joint, but we are making this in this flexible joint system. So what you can see here is that this gray thing is our actuator. So if it pushes, the wing goes up, and then when it pulls, the wing goes down so that we can generate flipping the rotating motion of the wing. And also, the second system is we have like compliant hinge structure on the base of the wing. So what we actually do is that we have this hinge structure's stiffness plus wing's inertia so that it has its own natural frequency of the flapping. So what happens is that during the rotation of the wing, we also have flapping motion of the wing, which actually generates the thrust. So we totally have like 2 degrees of freedom motion in the system, but since we can put this resonance mode into the same frequency, we can achieve those two motion with only one actuation. So I would say this is very efficient system design. So this is how our robot moves. So you can see our DEA in the center, actuator in the center moves linearly, and then all the joint converts this linear motion into rotation. And then you can also see the wing is not fixed, but it's flapping through the rotating motion. So right now, what you can think is that the robot is generating the thrust behind the screen. So I say robot is doing 부채질 in Korean, it'd be towards behind the screen. And then right now, the operating condition is like 1400, 1.4 to 2 kilovolts, and then around like 400 hertz. So typically, if I introduce this voltage, it's very, astonishing to normal researchers. But since you're all familiar to DEAs, it's pretty typical in DEA field, I guess. So if you take a look from the sideways, it looks like this, just like what we intended. So this is something like ideal motion from the sideways, and then this right now is generating thrust downwards. So if we clamp it to lift off stand, the robot can start lifting off. So right now, this actuator with pair of wing, you can think it as a motor with a propeller. So what we really need is that we need to put four of them together to make it into quadrilateral shape to achieve this controlled flight. So right now, this is the full robot with 4 units. And then what we can do is we can do the controlled flight. This is called hovering flight with a set point. And then this is golden standard for the flying that if we can do hovering, that means we can just move anywhere we want for the flying robot perspective. I'd like to go a little deep to our system. So this is our robot on the right side. And then we actually have like motion capture markers. And then this markers, due to this markers, our robot's 3D position and orientation can be captured by this Vicon system, motion capture system. So what we actually do is we actually have like off-board outside computer that runs all the controlled loop. And then the control signal feeds into the robot by going through this high voltage amplifiers. So I say our robot right now is doing off-board sensing, off-board control, and off-board power. So the goal for our lab is that we work all different aspects of our robot, structure, material, actuator, power system, and controls, plus battery, so that we can make our system something like commercial drones, meaning everything on board, everything by sensing, computation, and then power systems. So I'd like to discuss two features on robots. First thing is powered and soft artificial muscle, basically DEAs. And then the second thing is flapping wing structure design. So let me start with the artificial muscles. In fact, this flying robot design is not really, we are not the first one who really implemented or who really invented this flying robot structure. So it was actually this research has done within like 20 years so far, and then the most breakthrough robot I say is RoboBee in Harvard, especially from Professor Robert Wood's lab. And then from the RoboBee, there are all different types of like designs which use like different structures or different power systems. But the common theme for them was that they use so-called piezoelectric actuators down here. So piezoelectric material is like uh, it's the material that if it gets applied by voltage, it expands. So what they can do is they can make like two layers of piezoelectric actuators. So if you apply voltage to the upper ones, it bends downwards, and then if you apply voltage to the down one, it bends upwards. So this is called like bimorph style actuator. But there was some issue for this, that especially that piezo actuators were rigid. It was very lightweight and efficient that it can support like such a light flying robot systems. But it actually had the issue of being too fragile. So if it touches anything, if robot collides with anything, like the robot breaks, especially the actuator breaks. So it really limited the space of design configurations or design trials or control trials. So what we actually ended up is that we need new actuation mechanism that can be more robust than piezoelectric actuators. So what came into our mind is that we actually came to soft material actuators, which can be very delicate, but still very robust from this type of context. And more so, sometimes soft actuators are really demonstrating huge resilience toward damage, which is really something promising compared to piezoelectric actuators. Then what we actually need from those soft actuators, especially if we want to use those soft actuators for flight muscles, I think there are three main requirements. One is try to be compact because we are making small robots. And then the second thing is to be power dense. So power dense means it's not only have to be powerful, but it also has to be lightweight enough that it can support its own weight by generating thrust. So it has to be power dense basically. And then also the flapping is pretty like high bandwidth motion. So the actuator itself has to be high bandwidth as well. So if you roughly lay out all different types of transduction like thermal, pneumatic, magnetic, chemical, and electrical, we can briefly think the electrical fits pretty well of those among those all functional requirements. So this thing will be very familiar with all your lab members. So we use dielectric elastomer actuator structure, which uses like this elastomer with sandwiched by two electrodes. And then there are a ton of like DA studies so far, which sometimes uses this contraction in vertical way, sometimes use this stretch in lateral direction. And then for us, we especially use this rolled up structure into the cylinder shape. So I think the beauty of this rolled up structure is that by rolling the actuator, it constrains a little bit of like this radial motion so that we can concentrate the motion out a little into the axial direction, which can be more efficient for our robotic system. And then some property of DEAs, I think it's also familiar to your lab, but due to our elastomer, our actuator itself has pretty high natural frequency, especially in this structure, having like around like 500 hertz of natural frequency. And then if we measure block force, we have like 0.35 newtons around block force. So if we assume the linear, force to displacement relationship, we can briefly estimate the power density of our actuator to be 640 watts per kilogram. So sometimes I explain this number as, so 1 horsepower is 750 watts. So that means horses are generating 750 watts with their whole body weight of around like 300 kilograms. So you can briefly, imagine our actuator being like around like 300 times more efficient than horses. So it's not actually powerful as horses, but it's actually 100 times more power dense than horses. And from our previous results, you can also already see our actuator being very, very resilient to this contact, which is very distinguished, unique property from previous like piezo-driven actuators. For us, we are using there are multiple compliant electrode material candidates, and then we are using carbon nanotubes. And then for elastomer, we are using Elastocell P7670 elastomer due to its dielectric strength and then the frequency behavior. One important aspect of the structure is that we are using high electric field, which makes our life, a little not easy. What is really hard is that we are using high electric field of 60 volt per micron, which ends up being around like 2 kilovolts of voltage requirement. So far, I was emphasizing that our DEA can be much better than piezo, but if you start looking into electrical property, it's not true anymore. So if you see the operation voltage, actually our DEA is using like almost like 10 times higher voltage, and then power consumption is also way higher, whereas efficiency is not so much high. So mechanically, these are very promising, but electrically, there's still a huge gap between electric DEA and piezoelectric actuators. The other thing is breakdown. So this is the site, like the cross-section illustration of our DEAs. Sometimes, so since we are not making everything in clean room, and then although we make in the clean rooms, it's kind of unavoidable to have like some defects inside our DEAs. And then since we are using CNTs, the microscopic structures are not so much even. They have some sharp features like this. So if we start applying voltage, what actually happens is that the electric field is not identical among the surface, and those surface have they suffer from electrical breakdown, which ends up being the shorted path between those two layers. So this is a video that we observed electrical breakdown. We are keep applying voltage higher and higher, and then at some point you can see this huge burning occurring. And this is not only very scary, but practically what happens is that one failure can fail entire device. But still, during the fabrication, it's very hard to get away with all those defects. And then this really increased the chance of failure of whole device. So our roadmap for addressing those issues is that we first optimize DA material and fabrication so that we can make our actuator breakdown resilient. So after we obtain this breakdown resilience, we fabricate DA with much thinner elastomer layer thickness, which can ultimately reduce our operation voltage of our DEAs. So to be specific, what we find is that we actually focus a lot on this local burning part, especially that if we apply very moderate amount of electrical power in this local burning stage, what we can do is that instead of going to this electrical breakdown, we can actually isolate that area from the others due to the connection of CNTs. Basically, you can think it as CNTs are a bunch of rods connecting to each other, but if we apply very moderate amount of electrical power, they disconnect that local part from the other so that the other part can be still functional. So if you see this video, you can see this very short lighting up, but it suddenly goes down, which visually demonstrates this clearing effect, and then we call this effect self-clearing. So what is important for self-clearing is that we have to maintain the quality of the elastomer as much as we can, of course. And then what we're finding is the concentration of CNTs, so the amount of CNT we are using for the electrode is very important. And then the power input at the burning point is also important. So this is the graph, the blue and voltage, and then the orange and current. And then if we zoom it up, what happens is that the current instantaneously goes up, but it drops, which means the local burning is disconnected from the other parts in very instantaneous time constant. And then if we keep doing this process, it ultimately becomes very clean graph like this in the beginning of the plot. And then at the end, what we actually do is we actually apply AC voltage. So if we apply AC voltage and then measure this voltage relative to the current, this IAC over VAC value indicates R and C of the system, which indicates the status of basically our electrode. So it's very hard for us to observe the electrode directly, but we rely on this value to see if our actuator is okay or not, especially when we go to higher electric fields. So how do we improve elastomer layer quality? So this is the fabrication process of our actuator. We do the spin coating to make elastomer layers, and then we cure it, and then we do something called, we usually call it stamping. So we make the CNT layers on top of PTFE filters, and then we stamp it directly on top of elastomer with the mask so that we can get desired patterns. And then we do this multiple times until we get our desired thickness. What we firstly find is that doing a vacuum, seems to be a pretty simple process, but it had really like huge impact, especially for our system. So as I mentioned, if we monitor this IAC or VAC value by applying higher and higher voltage, what we find is that the sample with not vacuumed drops this value pretty quickly, whereas the sample with vacuum process maintains its IAC or base value toward higher electric field. And then since we are doing flying robot, we can basically explicitly draw this line for takeoff condition and the max lift condition. So obviously, if we don't do the vacuum process, we can't really get to a max lift condition. And then the second thing I mentioned before is the amount of CNT we're using. So this is a SEM image of like all different CNT concentrations. And then the typical impact of CNT is pretty clear trade-off that if we use more and more CNTs, it's better for having good conductivity or low resistance, of course. But if we use more CNT, it's hard to isolate itself from the defect areas. It's pretty apparent. You can imagine that well, if we have more CNTs, it's hard to isolate. You can also see that impact from this monitoring IC or VAC values that if we keep increasing the amount of CNTs, there is a certain range that it drops very quickly. That means the breakdown occurs too much that it damages our CNT layers before we get to our max lift condition. On the other hand, from our RC model, we can define the minimum conductivity or the maximum resistance we can afford to get our desired flapping motion. So this sets our minimum of CNT we can use. So from those two criteria, we determine our optimal CNT concentration. So after doing this, what we have done is we started making elastomer layer thickness thinner and thinner, basically by spin coating faster and faster. And then we reduced down the elastomer thickness from 335 micrometer to 10 micrometer, which let us use the voltage from 2 kilovolts to 630 volts, with still the endurance over 2 million cycles. And then you can still think like 630 volt is still high, but we actually demonstrated that 630 volt is something we can afford with this like 0.1 gram circuit. So basically this opened up the domain where we can actually try power autonomy for our robot. So even more than that, from this like high performance fabrication of actuators, we want even higher, we want even more successful demonstrations such as damage resilience. So several questions we can ask is that if the robot will be able to fly with severe actuator damages, or if there's already the damage occurred, can we repair those damages? Or is the actuator robust enough to withstand structural damage, something like the wing damage you are seeing in the photo? Our finding is that, so if you take a look at our self-clearing process, it's basically if there's like local burning, we can isolate them from the other network, CNT network. And then our finding is that this is actually applicable to external damage like piercing damages. So if we have like piercing damage across our DEA, what actually happens is that if we apply like moderate amount of electrical power, we can isolate that piercing from surrounding CNT networks. which lets out. Oh, um, uh, so if you see the video over here, you can see there's like local burning happening, and when where the needle is piercing the DA, but it also instantly goes off, which indicates the self-clearing process from the piercing damages. So even more so, what we can do is we can pierce more and more needles. It's the piercing by 10 needles. And then the reason we stopped at 10 needles is that there was no more space that I can put the needles anymore. And then you can see it's also withstanding the wing damage, which indicates that DA is resilient enough to withstand asymmetric aerodynamic loading in different sides. And then this was even able to liftoff. So basically DA maintaining the power density that can support the flight. The other thing we demonstrated here is that sometimes there is already the case where the DA is already suffered from breakdown, basically breakdown already. And then what we actually found out is that from our 3D view, what we can do is that we can actually isolate or isolate that area with the UV lasers. So over here, what we actually do is that we actually isolate this area using the UV laser. And then what actually happens is that this laser penetrates through the elastomer because the elastomer is relatively transparent, whereas it locally degrades the CNTs. So if you see the proper case scenario, you can see there's a light region from the CNTs where CNTs are not fully gone, but still degraded. So the next step, what we can do is we can apply high voltage so that we can clear out that degraded area of CNTs, which will ultimately give us isolate the defect. So what actually happens is that if there's some failure occurred inside our robot, what we can actually do is we can actually take out the DAs. We're doing rolled up DAs, so we have to unroll the DA, which is a little bit manual process. And then at the end we put it into the laser, and then we can encircle that defect area, which you can see the circle here, and then we can roll it back, and then at the end we can put it into the robot, and then we apply high voltage to find fully isolate the defect, and then at the end you can see the robot flipping. So basically recovers its flipping um, functionality. So this is the characterization, which all suggests that there is a degradation by putting needles, but which still can afford the flight level power density. And then Um, we finally we constructed a robot with four robots which suffered different kind of damages. So this robot suffered from 10 piercing with damaged wing, and this robot suffered from laser recovery. And then at the end, we put all of them all together in the same robot, and then you can see this robot is still capable of doing hovering flights. And I say this is very like unique from like commercial rigid type actuators. Even in electromagnetic motors, you can't really imagine like motor getting pierced but still being operational. So I'd like to move on to second part, switch gear a little, which is flipping wing structure design. So this is the robot structure you've been seeing during my presentation so far. Then the issue in current design, whenever we submit the papers and then whenever we get the reviews, there are typical reviews that we are getting. First of all, many people have told us that robot's a little ugly, especially this down version. This Many people treat this not as a single robot, but it's something like four men carrying some object or something. So we actually get a lot of like comments that our robot is ugly. And then, but more practically, we actually had inefficiency, especially in the inner wings, that the wings are too close to each other, so they have like aerodynamic interference with each other, which ultimately reduces the total lift we can generate. And then the other thing is compactness. So say if we want to make our robot like fully autonomous, which will need like board and batteries, we can't really obviously utilize this space, which is ultimately the problem. And then also the lifetime. Actually, the longest lifetime this robot was able to fly was only 40 seconds. Some parts were breaking, especially the wings were breaking pretty often. So if one wing breaks, we have to repair one wing, and then if we fly for 10 seconds, then the other wing breaks. So those are all the issues that our previous robot had. So the solution we came up with is simply to cut the robot into half and then just throw out all the inner parts and then put this 4 units with the half of the robots. So the plan is to make it into half, to ground the robot from the half, and then put 4 of them together to make the quadrilateral shape. But this looks pretty simple, but it was actually practically not as simple as we thought in the beginning. Some issues occurred that right now, the structure had like actuator suspended by 2 transmission, whereas this structure, the actuator is applying force directly to the airframe. So the airframe started to shake a lot. So we had to reinforce the airframe, which led the airframe became more heavier. And so we had to afford more weight, which we ended up increasing the wing size. And then some other factors like the transmission was suffering from like off-axis motions. So we added like guiding structures. So the top parts are the previous robot, and then the bottom parts are new design. So you can see the actuator length got into half, but still we need larger force. So instead of using 6 layers, our new actuator used 10 layer, which can produce more force. And then you can see the airframe was reinforced by a lot. It's smaller, but still heavier. And then this is like this airframe is like 12-piece assembly with all this I-beam structure so they can be very resilient from all the oscillations. And then the main problem of our robot was actually the wing hinge. So this is the flapping motion where wing hinge has failed. You can see this is pretty often happening that our wing was flying off during our flapping kinematics trial. So this is even worse if we observe it during flight. So this is like hovering flight and the wing goes off and the robot really crashes to the bottom, which is very scary, especially if you want to write paper with this robot. It's very, very scary scenario, you know. And then the reason actually we found out that this wing hinge breaks a lot was that the center of pressure, the wing was getting the pressure pretty off from this wing hinge location. So wing hinge is from here to here, but since the center of pressure is like off axis by 5.5 millimeter, the wing hinge was actually getting a lot of like torsional stress, which ended up giving the stress concentration in 2 corners. So we changed the wing design so that it can be a little larger, and then we elongated the wing hinge along the edge so that the center of the wing hinge and the center of pressure can be aligned pretty well. So due to our console simulation, actually the stress concentration has dropped by almost like 100 times. And then this wing was able to made by laminating this 7 different layers with 4 different materials. And then the other thing is transmission. So if you see this motion a little closer, the actuator is supposed to push and pull in lateral direction, but you're seeing a lot of like up and down motion, which is like tracked by this small red circle here. So this is actually coming from the fact that the actuator was not able to mitigate the reactional force from wing and transmission. So what we actually made instead is that we put 2 guide transmissions that can apply counter stiffness to that off-axis motion. And then at the end, if you compare the motion, you can see by putting the guide transmissions, the actuator is moving much more linearly than the original case. Especially if you think of the system where the lateral motion converts to rotation, it actually obtains a lot of efficiency, especially in our flying robot system. So combining all of that ended up being 180 milligram robot unit. And then by combining 4 of them, we can construct like 750 milligram robot at the end. So we do all the flapping kinematics test, and then Now, what we can see here is that our actuator has like natural frequency of like kilohertz, but due to having wings and all the weight, our natural frequency of the system, oscillation frequency, ended up being 300 hertz. But there's some compromise between flapping fast versus flapping large. So our flapping frequency ended up becoming a little larger than this 300 hertz with 330 hertz. This is the lift-off test, lifting off 360 milligram with like 180 milligram robot, which tends to be 2-to-1 lift weight ratio. And then we do a little bit of like hinge stiffness characterization. We defer the hinge stiffness by deferring that the hinge joint structures, and then we maximize the lift by having appropriate hinge stiffness. So this is hovering flight for new robot. And then right now, what you're seeing is that this is hovering flight for 1,000 seconds, which is basically 2 orders of magnitude increased from previous robot, around like 20 seconds to 40 seconds. So this is due to all the small parts improvements. And then we got to huge increase in our flight time. And then this is demonstration. As I mentioned before, if we can do hovering, we can do whatever trajectory we want in 3D space. This is following the trajectory of MIT pretty closely. And then this is basically a demonstration where we can really just command whichever trajectory we want and then get it to the set point. Even more so, we can really follow complex trajectory in 3D. I don't know if you can hear the sound, but this is actually how our robot sounds like during its flight. And then right now it's following pretty complex 3D trajectory, which is like widely used in drones, trajectory following characterization as well. And I'd like to show this video doing flip. I mean, this is real time. You can almost see nothing from the real time, but if you can take a look at the slow motion video, what the robot actually does here is that it firstly ascends, and then it flips its body in the air, saturates, and then comes back to the original position. So this is very acrobatic motion, very unique from like commercial drones. Commercial drones almost cannot do this, or very, very hard to achieve these motions. And for us, actually, what we have to mention is that we were able to do this before as well with our previous robot design. So if you see this video, this is doing same flip, ascend, and flip. But what actually happened from this robot was that this robot didn't have enough thrust, the total thrust that it was not able to mitigate its thrust loss during the flip, and then it had to bounce off from the ground. Whereas if you watch our new robots flip again, it's flipping much faster, and then it has much higher lift that it can balance itself, not bouncing off from the ground. Even more so, what we can also demonstrate is double flip, which is really rare from drone society. So again, in the real time, we can't really see much things in real time, but if you go to slow-mo, you can see the robot flipping twice in the air, and then but still can saturate without bouncing off from the ground, and then comes back to its original position. And then if we back calculate our rotating speed, actually, this is our work during double flip. We actually compared the results of the flip with all the flipping speed of existing aerial robots plus natural insects, and we figured out that our robot was actually faster than any of the insects in nature. So to summarize, we reduced the number of wings by 4, and then with the max flight time increased by a factor of like order of 2, and then the rotation speed was also increased by 4 times for the new design. So this is part of summary that I like to give the summary by giving this heritage of this research. So the breakthrough of this research happened in 2013, whereas this railway was achieved controlled flight for the first time. But the issue here was the actuator being too fragile. So actually, this is Professor Robert Wood at Harvard. And then this is my advisor, Kevin Chen at MIT, back then in PhD students. And then firstly implemented the soft actuator to the robot to make the robot more resilient to damage. But still, we started facing the voltage requirements to be too high. So, as I joined the group, I started working for lowering down the voltage, which I lowered down to like 600 volt-ish, which is now around like I would say like 400 to 500 volt for now. And then we faced the next issue of like structural lifetime being limited. And then the new design has overcome that issue. And then the rest of the effort we try to make is really to put all the power system and sensing system on top of the robot and then make the robot be able to support that whole payload. So this is the short future. We envision a lot of like applications of the small things flying, such as like artificial pollination, natural monitoring, or search and rescue missions. And then also in terms of academia, since we are doing a lot of different aspects of our robot, we hope that we can collaborate with all the different researchers in the field of like sensors, material science, aerodynamics, mechanical design, and advanced controls. So I would like to thank to all my like my professor and all my friends. And then today's presentation summarized mainly three papers here. So if you want some details, you can later on look at those three papers. And thank you for listening.
어, 일단 먼저 박수를 드려야겠네요. 박수. Yeah, please
감사합니다.
keep him big hand. 예, 제가 곧 일어나야 돼서 일단
예.
말씀드리고 싶은 게 제 개인적으로 다이렉트 일러스토머 관련해서 연구를 오랫동안 해오기도 하고 봐오기도 됐지만 다이렉트 일러스토머 관련해서 들은 발표 중에 예, 역사상 가장 좋았던 것 같아요.
어,
그래서 네,
감사합니다.
예, 정말 너무 훌륭한 발표였고 특히 뭐 단순히 연구 결과가 좋은 것만 이야기하신 게 아니라 다이렉트 일러스토머를 이용해서 구동기를 만드는 모든 연구자들이 고민하고 있는 문제들을 굉장히 구체적으로 언급하시면서 그에 대한 솔루션을 제시하신 게 연구적으로도 너무 훌륭하시고 또 교육적으로도 너무 많은 그 관심 있는 모든 사람들에게 큰 도움이 될 것 같아서 네, 그 저희 학생들에게도 저희 연구실에서도 이게 기록으로 남아 있으면 아마 향후에 관심 있는 학생들에게도 제가 꼭 들어보라고 뭐 밖으로 공유하진 않겠지만 연구실 안에서 교육을 위해서 꼭 들어보라고 할 정도로 연구적으로도 너무 훌륭하고 교육적으로도 저는 너무너무 훌륭한 예, 제가 본 것 중에 예, 최고의 발표였던 것 같습니다. 그리고 저희
예뻐.
예, 학생들이 많은 관심이 있을 테니까 좀 경험에 기반해서 많은 조언들을 해주시면 고맙겠습니다. 제가 나중에 다시
아,
한번 연락드릴게요. 너무 고맙습니다.
예, 교수님 감사드립니다.
감사합니다.